The goal of this discussion is that by the end of it, you should have a good understanding of how to go about naming aromatic molecules. Specifically, we're going to be focused on molecules where we have a 6-membered carbon ring with alternating single and double bonds. So we're talking basically here about derivatives of benzene. So looking at this list of different aromatic molecule parent names, you'll see that the parent names of aromatic molecules are going to be derived from the functional group that is bonded to the ring, where phenol has a hydroxy group bonded to it. The OL there is a clue that we have an alcohol. Toluene has a methyl group. Benzaldehyde has an aldehyde group or CHO group there directly bonded to the benzene ring, and so on and so forth. Each of these structures is shown to you in a handout that is available on Canvas. If you look in Canvas under Files, you'll see this exact handout. I definitely encourage you to download that and use it for reference. You are expected to know each of these names and be able to apply them on exams, quizzes, and things like that. So get familiar with these names. One way to do that is certainly with flashcards. So we're going to be applying today these parent names up here at the top to enable us to come up with complete names for more complex structures. So we don't just have one group coming off the aromatic ring, but we have more than one group coming off the aromatic ring, or more than 2 groups coming off the aromatic ring. We will also today be talking about developing the names when we are dealing with aromatic rings as parts of larger molecules. So if we want to try to refer to the aromatic ring portion of a larger molecule, we can refer to a phenyl group, PHENYL, or an aryl group. Those are synonymous with one another, and that is if we want to specifically refer to just the aromatic ring portion of a larger molecule. We also have another term that we can use where we are referring to the aromatic ring plus 1 carbon coming off of that ring. So if we're trying to refer to the aromatic ring plus 1 carbon coming off of the ring, we refer to that as a benzyl group. So the benzyl group is the aromatic ring that we see here, plus the first carbon coming off of the ring. And we refer to that first carbon coming off of the ring as the benzilic carbon. So the benzilic carbon, shown here, is the first carbon coming off the ring. The hydrogens that are bonded there are called the benzilic hydrogens. We'll get into more on that later. The benzilic position we're going to see has special reactivity, and that's why one of the reasons why we have a special way of referring to that. So the benzilic group is the aromatic ring plus that first carbon. If we're referring to the benzilic carbon, that's just the first carbon off of the aromatic ring. So getting back to going about naming organic molecules that have aromatic rings, let's talk about the situation of having more than one substituent coming off of the ring. So we're going to come up with names that feature the parent names that we see up here at the top and have prefixes to indicate the other groups that are bonded to the ring. And also we will need to indicate where those groups are bonded on the aromatic ring. So if we take a look at the possibilities here, when we talk about disubstituted aromatic rings, we have 3 possible constitutional isomers that we could make. We can make a constitutional isomer where R, which is whatever group we want bonded to the ring, and R prime, our second group bonded to the ring, are on adjacent carbon atoms. So we could call that a 1,2 substituted aromatic ring, because the 2 groups of interest are on adjacent carbons, carbon 1 and carbon 2. As a constitutional isomer of this, we could put our 2 groups at carbon 1 and carbon 3. So rather than 1,2 substituted, we call this 1,3 substituted. And then as a third constitutional isomer, going on around the ring with that R prime group, we could put the R prime group right over here. And we call that a 1,4 substitution, because if we look at the ring and we say that this is position 1, going around the ring in the shortest direction, which either way here is going to give us the same distance, would put us at position 4 for the second group. So these are going to be our 3 constitutional isomers that we can make by bonding a second group to the aromatic ring. And you would see that if you continued on around the ring, for instance, if we say, took and extended this a step further, and we had our original R group as listed, and then moved the R prime group from position 4 over here, what you would see is that this structure would again be a 1,3 substituted structure. So it would be exactly the same as the structure that we saw here. So there are only 3 possibilities here. The 1,2 substituted, 1,3 substituted, and 1,4 substituted. So 3 possible constitutional isomers that we could create out of a disubstituted aromatic ring. And we have special names for each of these 3 substitution patterns. Those special names that we use for the 3 substitution patterns are ortho, which refers to having the 2 groups on adjacent carbons. So anytime we have a 1,2 substituted molecule, we would describe that as ortho, where this is position 1, position 2, going in the shortest direction to get to the next substituent, takes us right to there. So that's 1,2 substituted. A second constitutional isomer we refer to as the meta-substituted constitutional isomer, and that's going to be a 1,3 substitution. So position 1, going in the shortest direction to get to the next substituent, we put the second substituent at position number 3. So that's ortho, meta, and then the third constitutional isomer is referred to as the para-constitutional isomer, and we'll see that that's a 1,4 substitution pattern here, going around the ring. So our 3 constitutional isomers, anytime you have a disubstituted aromatic ring, are going to be referred to as ortho, meta, or para, and we'll use these terms in the name in order to indicate what constitutional isomer we are referring to. So let's take a look at applying this knowledge toward an example problem or two. So as our first example, we'll have an aromatic ring here. Like so. And we're going to come up with a name for this. So if we look back at those possible parent names, one of the possible parent names you will see is phenol, referring to an aromatic ring with a hydroxy group directly bonded. And so we'll go ahead and write the name in here, phenol. And looking at the substitution pattern here, we see that the phenol group, the parent group, is always listed as being at carbon number 1. Go in the shortest direction around the ring, takes us to carbon number 3. So it's 1,3 substituted, so we'd refer to this as meta with the prefix. And then we need to indicate that at that meta position, we have this group, which is an isobutyl group. So we'll call this meta isobutyl phenol as the full name of this molecule. A constitutional isomer of that would be if we had still our phenol group there, but rather than at position 3, say we had our isobutyl group at position 4. 1, 2, 3, 4. Now we'd refer to this, rather than as being the meta constitutional isomer, we'd refer to this as the para constitutional isomer. So everything about the name would be the same here except para instead of meta. So para isobutyl phenol as the name. There is one other acceptable way to refer to these, and that is you could refer to it using numerical based substituents. So rather than saying meta isobutyl phenol, you could also refer to it, if you wanted, as 3 isobutyl phenol. So it's always assumed that the substituent coming off of the ring at position 1 is what lends to the parent name. So it's assumed that at position number 1 here, that is always going to be where the hydroxy group is, since the parent name is phenol. And then going around the ring in the shortest direction puts us at position 3. Carbon number 3 of the ring is where the isobutyl comes off, so that's why we could call it 3 isobutyl phenol. By far the most popular way to go about naming these is using ortho, meta, and para, but certainly it is acceptable to also alternatively use this numerical nomenclature instead. That is totally fine. So let's take a look at coming up with a name. For this one, if we were coming up with numerical nomenclature here, it'd be 4-isobutyl phenol. So hopefully not too bad. The main thing is lock into your mind the ortho, meta, and para. We're going to move on to a couple of other example problems here. So let's say hypothetically, we had this chemical structure. So looking at this, if we go back to our chart here of aromatic group names, you will notice that in our aromatic group name, in our aromatic group structure, we had an aldehyde group. So our parent name here, as a result, will be benzaldehyde. Our CHO there is our abbreviation for an aldehyde. So we've got our aldehyde group here. So our parent name is going to be based on that aldehyde. So our parent name is going to be benzaldehyde. And then our prefix here is going to be ortho, since the two groups, the two substituents, are on adjacent carbon atoms, so ortho dash. And then the group that we see here, NO2, is referred to as a nitro group. So we're going to refer to this NO2 group always as a nitro group. And nitro groups are very commonly seen in aromatic molecules. So commit that to memory that NO2 is a nitro group is the name of that. So ortho-nitrobenzaldehyde, this would be written as one word. I left a little bit too much space there, but do be aware nitrobenzaldehyde is one word. So what about if we run into the situation where let's say that we have a molecule like this, where if we look back at the parent names, we will see two possibilities for parent names. We will see the possibility that this could be referred to as a phenol ring, since we certainly have a hydroxy group there bonded to the ring. We would also see that it could be referred to as a toluene ring as the parent name, because there's also a methyl group bonded there. So how do you decide which one to use? The answer here is that actually it is acceptable to use either of those as the parent name. So the two possible names here would correspond to having a parent name of phenol or a parent name of toluene. And either one will work here. We just need to adjust the prefixes accordingly. So if we go with the parent name phenol, we'll notice that we have a 1,3 substitution pattern. So this would certainly be a meta constitutional isomer. So we refer to this as meta methyl phenol, since the methyl group is at that meta position. Methyl phenol is one word. Or alternatively, we could refer to this as meta hydroxy toluene, because our hydroxy group is located meta to the methyl group. So either one of these two names will work here, and that's going to be true anytime that you have two possible parent names based on the image above of all of those parent names that we saw. If there's two on the chart that could be used, it is acceptable to use either. Whatever one you don't choose will become the prefix here. The final situation we need to talk about when naming aromatic molecules is what if we have an aromatic ring that has more than two substituents on it? What will we go about doing there to come up with the name of that molecule? So we're going to look at greater than two substituents on the aromatic ring. And if we're talking about the situation where we have multiple, more than two substituents on the ring, we're no longer going to be able to use the ortho, meta, and para at all. Instead, we're going to be stuck using numerical designations of the location of each of the substituents on the ring. So don't use ortho, meta, or para at all if you're dealing with 3 or more substituents on the ring. Instead, you're going to have to use numbers. So in order to go about doing this, let's take a look at an example problem here. So we're going to take a look at a situation where we have our aromatic ring. Like so. And what you'll want to do in this situation is figure out what you want to use as the parent name. And like we saw in the examples above of the disubstituted aromatic rings, sometimes there will be more than one possible choice here for the name of the parent group, and that is totally fine. Pick one. So in this case, phenol is what I'm going to choose to use as the parent name here. And then relative to that phenol group, the phenol group has to be at carbon number 1. We want to go in the direction to put the next group on the lowest possible carbon number. So we'll number clockwise here to end up having a group at position number 2. If we'd gone counterclockwise, we would have had to go all the way around to position number 4 in order to get to a group. So we're going this way clockwise because that'll put us at our second group as soon as possible. So going on around the ring, I'm going to number each of the carbon atoms in order here. And we see that our substituents are at positions 2 and 4. And specifically at positions 2 and 4, we have an ethyl group at position number 2. So we refer to this as 2-ethyl. At position number 4, we have a propyl group, so we call this 4-propyl. Plug in these names in alphabetical order like we usually do when naming prefixes, and we will be good to go here. So ethyl comes before propyl, so I'm going to go ahead and put in the ethyl group first. So 2-ethyl. And then secondly, I'm going to plug in our 4-propyl. So 2-ethyl 4-propyl phenol is going to be the complete name for this particular molecule. As one final example here, let's take a look at another structure and come up with the name for it. We're going to throw in some of these nitro groups here, which I said was really common to see nitro groups showing up in aromatic molecules. All right, so we've got this set up here. And taking a look at this structure, we need to come up with a parent name for it. And the structure that I see from our figure above is an aromatic ring with a methyl group on it we can refer to as toluene. And so carbon number 1 of our ring is going to be that carbon that has the methyl group coming off of it. Here we have either what direction we could go. We'll hit a substituent with carbon number 2, 3, 4, 5, and 6. So we have 3 nitro groups here, here, and here, and those are at positions 2, 4, and 6. So we'd call this 2, 4, 6 tri, because there's 3 of them, nitro toluene, and the trinitrotoluene is all one word there, and that would be the complete name for this. So 2, 4, 6 trinitrotoluene. The 3 nitro groups are accounted for by the trinitro part. Toluene accounts for that methyl group. And our numbers here have indicated the physical location of each of those nitro groups. And if we take a look at the term trinitrotoluene here and turn it into an acronym, what we get is tri-T N nitro T toluene. This compound is more commonly known as TNT, the explosive. But we could certainly come up with our systematic name for it, which is the basis where the acronym comes from. So that about covers going about naming aromatic molecules. In the next unit, what we're going to talk about is some of the special reactivity that we're going to see at the benzilic position of aromatic molecules, that is the first carbon off of the aromatic ring. And then once we get into the next chapter, chapter 22, we're going to talk about reactions that will give all of these crazy substitutions on rings. So how are we going to go about doing things like making trinitrotoluene? How would we start with benzene and attach the nitro groups onto the aromatic ring? So that's what's coming up, and we will go ahead next up with reactions at that benzilic position and see what we can do there in terms of the chemical reactivity.